Welcome back to the deep dive. Today, we're jumping into some really fascinating field notes. Notes on fish keeping, part 151.
Right, very specific. A deep journal, really.
Exactly. Charting these experiments, trying to create sustainable aquatic environments. And our mission here is to kind of cut through the day-to-day stuff and pull out the key lessons about growing aquatic plants when conditions aren't perfect.
That's it. And looking at these notes, the ambition is, well, it's really clear. The user was trying to use lots of different aquatic plants, not just for looks, but specifically to improve water quality naturally.
Like building a little self-sustaining ecosystem.
Pretty much, yeah.
Yeah.
Trying to mimic, robust native environments. And they tried this in tanks, indoors, but also in outdoor ponds, which is where it gets less predictable.
Okay, so for you listening, here's the puzzle we're really trying to piece together. Why do some of those really popular floating plants, the ones you see everywhere, why do they often just completely fail when you move them outside? We're looking at why these changing microclimates can be such a challenge for certain species. So the main goal, as you said, sustainability through diversity. That was the driver. This person wanted specific plants, the ones known for soaking up nutrients.
Nutrient sinks, yeah.
To really thrive and stabilize the whole system.
Yeah.
Less need for chemicals.
And it's the outdoor part, the ponds, that really gives us the most interesting data, because that's where the plan hits snags. Right. We talk about environment generally, but here it's about microclimates. Outdoors, you've got, temperature swings, surface heating up, cooling down.
And shifting shade, I guess.
Yeah.
From trees or buildings.
Exactly. Localized shade. And the notes really bear this out. The difficulty came from these varying conditions. Just proved too tough for quite a few species to really get established long term.
Okay, let's unpack that. If the goal is improving water quality naturally, the failures are almost more important than the successes, aren't they?
In a way, yes. They tell you what the limits are.
So which plants were the canaries in the coal mine here? The ones that just wouldn't grow?
Well, the notes point to what we can probably call the challenging trio.
Okay.
These were water lettuce, water chestnut, and frogbit.
Ah, okay. All pretty popular, visually striking plants.
Very much so. And highly desired because they can be such aggressive nutrient absorbers, provide good cover. But their widespread failure here, it signaled a real fundamental mismatch with the setup.
So we know which plants failed. But why? What was the specific issue the notes identified? It wasn't vague, was it?
No, not at all. The notes are actually crystal clear on this. The attempts to grow these three, this challenging trio, they were largely unsuccessful, specifically because of a lack of full sunlight exposure.
Light. Not nutrients, not pH, light.
Light saturation was pinpointed as the absolute barrier they couldn't overcome.
Okay, and let's talk about why these plants are so needy when it comes to light. Water lettuce, for example. It's a big plant, grows fast. Why is it so much more dependent on intense light compared to, say, smaller floaters?
Well, it really comes down to their structure and their whole growth strategy. Big surface floaters like water lettuce, water chestnut, they're built to grab huge amounts of light energy quickly. They need it to support that large size, that rapid growth.
They float high in the water too, right? To catch the sun.
Exactly. They need that intensity to drive photosynthesis super fast. That's how they outcompete algae and process nutrients quickly. If the light drops below a certain point, a saturation point, they just can't generate the energy needed.
So they don't just slow down, they actually fail.
They collapse, yeah. Whereas smaller, maybe more flexible plants, they can often tolerate shade spells much better.
That's a really key distinction.
Yeah.
Slowing down versus just collapsing. Now, the notes had a little detail about frogbit, didn't they? It was grouped with the failures, but there was something else mentioned.
Yes, that's a fascinating little nuance. The notes mention minor success with frogbit, but crucially, it never achieved what the user called robust growth.
Okay, so what does that tell us? That tiny bit of success.
It suggests the setup was right on the very, very edge of being viable for it. Just barely. Frogbit is a bit smaller, maybe slightly tougher than water lettuce, but still needs a lot of light.
So it survived, but didn't thrive.
Exactly. Minor success probably means it got the bare minimum light, maybe just during peak summer, But the light wasn't intense enough or sustained enough for it to really take off to get into that exponential growth phase.
Stuck in plant purgatory, basically.
Kind of, yeah. It wasn't really contributing much to the overall goal of water purification.
Okay, this is where the comparison becomes really useful, because not everything died. Let's switch gears to the plants that actually did well. The hardier ones. Which species achieved robust growth, even in those tricky outdoor spots?
Right, so the champions here, the ones that the notes clearly state thrived, were Water Sprite, common Salvinia, and Duckweed.
Ah, okay. Water Sprite can be submerged or floating, right? And Salvinia and Duckweed are classic floaters.
Correct. And their success proves the basic conditions were okay. The water chemistry, the nutrient levels, the general temperature ranges must have been fine.
So the water itself wasn't the problem.
Doesn't seem like it. If we connect the dots, the contrast is pretty stark. You've got Water Sprite, Salvinia, especially Duckweed doing great, showing the environment could support life, even abundant life.
But then the complete failure, more or less, of the water lettuce group.
Yeah, it highlights a massive difference in specifically light requirements. Duckweed, for instance, it's tiny, it reproduces incredibly fast, and it's just much more forgiving if parts of the surface get shaded temporarily.
Way more adaptable than a big water lettuce plant that needs sun everywhere all the time.
Pretty much. So this whole experiment's not really a story about bad water.
It's a lesson in plant zoning, based on sunlight needs.
That's a good way to put it. Yeah, it's about solar energy demand. The setup could support growth, but only for species okay with moderate or inconsistent light.
The high-demand floaters, they needed something more specialized.
Absolutely. So the core lesson, the real nugget we extract from this deep dive, is that growing those demanding species successfully really hinges entirely on light saturation, achieving it and maintaining it.
It's the gatekeeper.
It really is. For that specific group of plants, light is the gatekeeper, which means for anyone trying to use plants for serious natural water improvement, you either pick species that match your actual light conditions, or you have to change the conditions.
And the notes show the user learned this lesson, right? They laid out a future plan based on this.
They did. A very clear, disciplined plan. The user decided they'll only try growing those challenging species again if and only if they set up an outdoor pond or feature that guarantees full sunlight.
No more compromises on light for that trio.
Yeah.
They learned it just leads to failure.
Exactly, and this is where we get the ultimate benchmark from these notes. The user defines the required light level by saying the future setup must be good enough for a lotus plant.
Wow, okay, setting a lotus is the standard. That's serious. That's a high bar.
It absolutely is. A lotus isn't just like sun, it needs intense, prolonged sun.
So what does using a lotus as the litmus test really imply? Beyond just hours of daylight?
It implies consistency and intensity, like you said. A lotus typically needs, 7-8 hours of direct, strong sunlight every day to really flower and thrive properly.
Right.
So if a spot can support a lotus, it means no significant shadows moving across it during the day, no tree canopy issues, no building shadows during peak hours.
It probably also implies a larger, maybe deeper body of water too, right? For stability.
Often, yes. Greater surface area, maybe more depth, which helps buffer temperature swings. Things tend to be more stable overall. So by setting that lotus standard, the user is essentially saying, I'm only trying water lettuce again if I can guarantee the absolute maximum solar exposure, taking light completely off the table as a limiting variable.
It defines a level of certainty, environmental certainty, that the previous setups just didn't have.
Precisely.
Okay, so let's wrap this up. What's the big takeaway for you, the listener, from these Notes on Fishkeeping, Part 151? It seems pretty clear that using diverse plants for natural water improvement isn't just about plopping them in. It's about meticulously matching the plant to its specific solar needs. You've got a spectrum now, right? From the more tolerant Water Sprite and Duckweed, all the way up to this demanding full sun requirement benchmarked by the lotus.
Use that spectrum to choose wisely for your own setup.
Know your light levels first.
Absolutely. And, thinking about this light-focused insight, it raises another interesting question to ponder. The original goal was emulating a native environment, right? And lack of full sun was the big roadblock they found for certain plants. So think about what else a lotus-ready pond provides, almost by accident.
Okay.
A spot perfect for a lotus often means it's sheltered from strong wind, maybe deeper, maybe has higher, more stable surface temperatures because of all that sun hitting it. So beyond just the light itself, what combined effect might these other stable characteristics of a lotus environment have? Could they be the missing piece for finally getting tricky plants like water lettuce or water chestnut to thrive consistently?
So the light might unlock other beneficial conditions indirectly.
It's possible that's the next layer to maybe explore. What else comes along with guaranteeing that full sun?